Hey everybody, Dr. O here, and in this video we're going to be talking about diabetic ketoacidosis and respiration. So let's get started. When we are performing respiration involving the lungs, it also involves a blood supply because what we're going to have in the blood supply coming into the lungs are going to be the carbon dioxide molecules. And what's waiting in the lungs are going to be the oxygen molecules. When we're talking about gas exchange, one of the things we need to understand is why the molecules are moving where they are. And the whole reason behind that has to do with the partial pressures of the gases. In short, it has to do with the population of those particular gas molecules in different areas. So, for example, the partial pressure of oxygen in the blood supply that's coming back to the lungs comes in at 40 millimeters of mercury, but over in the lungs, it's considerably higher at 104 millimeters of mercury. And because gas molecules want to behave very much like any other molecule, these molecules are going to go from an area where there's a lot of them or a lot of pressure into an area where there's not very many or where there's very little pressure. And that means that our oxygen is going to move from the lungs where the partial pressure is 104 into the blood where the partial pressure is only 40. So what's the story with carbon dioxide? Well, in the returning blood, carbon dioxide comes in with a partial pressure of 45 millimeters of mercury, and in the lungs it's going to be a little bit less at about 40 millimeters of mercury. Even though there's only 5 millimeters of mercury difference in the pressures, it's still enough to cause carbon dioxide to leave the blood supply and go into the lungs. Now that we understand the forces that are causing oxygen to move out of the lungs and into the blood and carbon dioxide to move out of the blood into the lungs, there's an important thing that we need to understand regarding carbon dioxide transport. So let's talk about carbon dioxide for a moment. So out in the tissues, this is where we are producing carbon dioxide. And carbon dioxide is going to enter into the bloodstream. And when it does, it's going to encounter water. And it's going to undergo a chemical reaction and it's going to combine to create a molecule called carbonic acid. Now, because carbonic acid is an acid, it has the tendency to cast off a hydrogen ion. So sometimes carbonic acid is going to exist as a molecule like we see here, and sometimes it's going to exist as its two ions, one of those ions being the hydrogen ion, and that hydrogen ion is going to contribute to acidity. So what we can say is that in the tissues, carbon dioxide has a tendency to live as carbon dioxide, but once it travels in the blood, it's basically going to end up acting as either a carbonic acid molecule or the ions of carbonic acid. So then the question becomes, what happens when the blood returns to the lungs? Because we don't exhale hydrogen ions and bicarbonate ions or carbonic acid ions. So what's going to happen? Well, what's going to end up happening is that this reaction is going to go in reverse. And that means then that our ions of carbonic acid can come back together and form a molecule of carbonic acid, and it also means that our carbonic acid molecule can actually be converted back into water and carbon dioxide. So then the short version of this is that once the blood returns to the lungs, it is actually going to be converted back into carbon dioxide by running this reaction in reverse. So let's look at this in a slightly different way. So we're out in the tissues. We've got some cells down here in the lower left. And the thing that we know about cells is that they're going to produce carbon dioxide. And here's the story with this chemical reaction we see on the screen. If we have a lot of carbon dioxide, that's going to have a tendency to drive this reaction to the right. We've got more carbon dioxide molecules than we have hydrogen ions over here. And so basically what we can think of is that we're going to feed these carbon dioxide molecules into this equation, and we're going to end up getting hydrogen ions at the end. So the body is basically trying to take carbon dioxide and find a way to transport it in the blood, and the way that it's doing that is by converting it into carbonic acid, and its ions. So what about carbon dioxide at the lungs? Well, there's one thing that we know about the lungs, and that is that the lungs are constantly eliminating carbon dioxide. So same sort of thoughts over here. We've got a lot of hydrogen ions on the right side of our equation, and because the lungs are constantly eliminating carbon dioxide, we don't really have any carbon dioxide on the left side of the equation. So we can think about feeding hydrogen ions into this equation and driving it to the left. And so when we feed our hydrogen ions into the equation, we're going to end up creating carbon dioxide molecules again. And because the lungs are constantly moving these out, we are basically managing this equation and eliminating the carbon dioxide and helping maintain blood pH this way. Now, because we're talking about diabetic ketoacidosis, we need to first of all understand a little bit about normal glucose metabolism. So what we have here on the screen is a mitochondrion, and the thing that we know about mitochondrion is that they perform what's known as aerobic respiration. And in short, what a mitochondrion is able to do is able to take an oxygen molecule and a glucose molecule and run them through some chemical processes and create some ATP and some carbon dioxide. That is normal glucose metabolism. But what if we don't have normal glucose metabolism? Well, let's have a look at that. So in the person who doesn't have normal glucose metabolism, we're not going to be able to use glucose and combine it with oxygen and the mitochondrion. So what do we use instead? Well, instead of glucose, the diabetic person is going to have to use fatty acids. And the reason for this is because either the person is not making insulin, which opens the door to let glucose in the cells, or the receptors for insulin are not working, which means we're not opening the doors for glucose to get into the cells. So then the diabetic has to look to another fuel source in order to produce ATP at the mitochondrion, and that's going to end up being lipids, fats, fatty acids. So our mitochondrion is going to take an oxygen molecule and some fatty acids, and it's going to run it through its chemical processes, and yes, it's going to produce ATP and some carbon dioxide. But here's the catch. In addition to producing the thing that we're looking for, it's going to produce a lot of additional molecules called ketones, and it's going to make a lot of them. And here's the problem with ketones. This is the molecular formula for a ketone. And the problem with this molecule is right here with that hydrogen. Because that hydrogen can come loose from that molecule and form a hydrogen ion, which is going to make the environment acidic. So now that we understand how the cells are producing carbon dioxide and the chemistry behind carbon dioxide transport and what's causing us to release carbon dioxide, let's put it all together in a normal setting. And now we've incorporated a chemoreceptor, which is going to be measuring the pH for us. So we're out in the tissues, and we're going to start there because our tissues are making carbon dioxide. And the thing we know about carbon dioxide is that it's going to enter into the bloodstream, and it's going to pass by a chemoreceptor, which is going to take a measurement of it. And the thing that we know about carbon dioxide is that it doesn't travel as the carbon dioxide gas. Instead, it's going to travel as hydrogen ions. And that's going to register with our chemoreceptor. And because this is normal respiration and normal functioning in the body, even though we're going to see a little bit of a drop in our pH, it's not going to be very much, and it's going to still be within normal range, and so we're good to go. And when this blood reaches the lungs are going to be doing normal respiration, which basically means it's going to easily get rid of carbon dioxide molecules and reduce acidity at a slow rate, just like normal quiet respiration would be doing. But what if we are in a diabetic ketoacidotic state? Well, let's have a look at that. So what about the person who is in ketoacidosis? Well, the thing that we know about them is that they are still making ATP, which means they're also making carbon dioxide. And because they are not using glucose, but are using fatty acids to produce this ATP, they're making tons of ketone bodies. And the thing that we know is that this carbon dioxide is going to enter into the bloodstream, and so are the ketones. The thing we know about carbon dioxide is that it doesn't travel in the bloodstream as the gas, it gets converted into hydrogen ions. And because ketones are acidic, so are they. So when this blood makes it past our chemoreceptor, it's going to put that dial into a dangerous zone. It's going to make us register as very acidic. And that's going to send a warning signal up to the brain. And the brain is going to say, we got a problem and we got to get rid of all of that acidity. So it's going to send a signal down to the lungs, and it's going to say, you need to increase your breathing rate and your breathing depth because we need to get rid of that carbon dioxide and the hydrogen ions that it represents as quickly as possible. Now, is breathing alone going to fix this problem? No, but it is part of the solution, and there are other body systems that are going to come into play to try to correct this problem. But this is what the respiratory system can do to help bring blood pH back up into a normal range. And with that, we are done. Thanks for watching.